In any case. Okay, so today we're going to be talking about the Poisson integral formula. Which we mentioned last time was related to this thing called the Dirichlet problem on the disk. Okay, so here's one way of phrasing it. Let f be an analytic function on and within a circle C naught, a radius R naught around the origin. Okay. And let U be the real part of that analytic function. Okay, so you have this harmonic function, right? The real part of this analytic function. Then for all R less than R naught, we have an expression U of R theta is the integral of R naught squared minus R squared U of R naught phi over R naught squared minus 2 R naught R cosine phi minus theta plus R squared d phi. So you can sort of get the idea of this. So when I'll use this sort of interchangeably. When I write U R theta, I mean U of R e to the I theta. It sort of depends on how you want to think of it. You want to think of it as a function of two variables or a function of one complex variable. Okay. But in any case, so this is when I write U of R naught phi. Well, that is U on the boundary, right? That is U of as phi goes from 0 to 2 pi, and at distance R naught from the origin. Okay, so this is recovering your function on the interior of the disk as an integral of something against the boundary values of your function. Okay, so you can guess what this is going to come from. This is going to come from the Cauchy integral formula. Right? It'll be some relative of the Cauchy integral. Okay. Let me say that we could rephrase this the hypothesis as follows. You could say let U be harmonic on an open set containing C naught and its interior. Okay. Right. Let U be harmonic on an open set containing C naught and its interior. Then for all R less than blah, U on the interior is blah blah blah. Right. Why? Well, because if U is harmonic on an open set containing C naught and its interior, then it's going to be harmonic on some slightly larger disk containing the circle, containing the C naught, right? And you know that that set being simply connected, you know that U is going to have a harmonic conjugate there, and so so there will be an analytic function for which U is the real part. So maybe this way is sort of more impressive, right? You start from here, but either way, it's basically the same thing. Okay. Given any harmonic function, you can reconstruct its values on the interior from its values on the boundary. Okay. And the authors do it in a slightly, phrase it in a slightly different way, which I'll mention later. Okay? So here's the proof. Like I said, this is going to be consequence of the Cauchy integral formula. It's basically like a polar coordinate form of Cauchy's integral formula. So let Z be R e to the I theta, where R is less than R naught, and let Z tilde be R naught squared over R e to the I theta. Okay. This point is called the geometric reflection or inversion of Z across C naught. Okay. So it has the same, you notice it has the same angle, right? It has the same argument, and the product of the moduli is R naught squared. So the picture is like this, right? You have your C naught, you have your, here's your C naught, right? You have some Z, and you have the reflection across it, Z tilde. Okay. So Z tilde is going to be something on the outside of that, on the outside. Okay. Okay. Then we just use Cauchy's integral formula. We say, well, f of Z then is 1 over 2 pi I integral over C naught f s over s minus c ds. Okay. Cauchy integral formula. Okay. And we're going to slide in another term, f of s, s minus z. I'm going to subtract off f of s, s minus z tilde. Okay. I'm going to say that we're not changing this at all. Why aren't we changing this? Why doesn't that change anything?
Z tilde is outside.
Z tilde is outside, right? So the winding number of C naught around Z tilde is 0, right? So this, right, 1 over 2 pi I f of s, s minus z tilde ds, well, that's going to be the winding number of C naught around Z tilde times the value of f at Z tilde, right? But the winding number is 0, so this is just 0. Okay, and then, well, let S be parameterized as R naught e to the I phi, where phi goes from, phi goes from 0 to 2 pi. We evaluate this thing, right? We get 0 to 2 pi, 1 over s minus c minus 1 over s minus c tilde, f of s, ds, ds is I r naught e to the I phi dphi. Right. Just evaluation. Right. In other words, we get I s. Right. This thing is your s. This is dphi. Right. And so you get 1 over 2 pi, right? The i's cancel out. You get s over s minus c, s over s minus z tilde, f of s dphi. Okay. Right. Nothing going on. If you work it out, you can see that this is equal to this plus z bar over s bar minus z bar. Okay. anyway, it's just an exercise. It's just a calculation. And what that gives you is 1/2 pi times what you end up when you multiply through is, of course, SS bar minus ZZ bar over S minus Z modulus squared. Writing that out, that gives you that f at z is 1/2 pi, being equal to 0 to 2 pi of r naught squared minus r squared over s minus c quantity squared f of s d. Right? Or actually, let me write it out without you. And so what we have is f of r e pi theta is that's what it looks like right now. Okay, and we just want to make this. We want to basically just get rid of the s's and the z's and translate everything into terms of r's and r naughts. Okay, so what we do is use the law of cosines. In fact, so if we have this point, this length is s, right? This length is s. This is phi. I mean, sorry. This is this point is s. This point is c. Sorry. Right, and we're wondering about the modulus of s minus z, right? This angle is theta, right? And so right, this length is r naught, right? And this length is r. Right? So you just use the law of cosines, and you say, right? S minus z squared equals r naught squared plus r squared minus 2 r naught r times the cosine of the angle, which is phi minus theta. That's the law of cosines. And so what you end up is this 1/2 pi r naught squared, sorry, it should be squared, r naught squared minus r squared over r naught squared plus r squared minus 2 r naught r cosine phi minus theta f of r naught e to the theta e to the I phi. So this is just the Cauchy integral formula expressed in polar form, right? F of r e to the theta equals this. and of course, this gives you the expression for u, right? U is going to be u of r theta. It's just going to be the real part of this, right? But the real part of this is you are not phi. And so that's the Cauchy. That's the Poisson integral formula. Let me just say something about what the authors prove. So the authors actually prove something a little bit stronger, which is if U is defined and continuous on the closed disk, on a closed disk, and harmonic on the interior, then for all r less than r naught, you have that formula. So same formula as before. So the only thing I want to say about this is that this is actually slightly stronger than what we showed. Okay. In the sense that what we assumed was that U was harmonic on a disk that was bigger than this. Okay. We assumed that U is harmonic on a disk that's bigger than this, and they're assuming that U is harmonic only on the interior and continuous on the boundary. Okay. So to get this sort of result is not that much more than what we did before, but involves the notion of uniform convergence, which we haven't talked about. So today we're going to talk about uniform convergence. Maybe after that, I'll give the argument. I'll give their argument. But this is more in the flavor of the Dirichlet problem, because for the Dirichlet problem, what you do is you start off with a function that's just defined on the boundary. Okay. You start off with a piecewise continuous function that's defined on the boundary, and you say, can you create a harmonic function on the interior of that thing, which approaches the boundary values as you approach the boundary? Okay, so this is maybe more in the spirit of things. So really, really what one would like to do at this point is say that. So just to, this is a little bit of a digression, but for the Dirichlet problem on disk. What you do is you define the Poisson kernel, right? So you define this thing, Poisson kernel. And then for any piecewise continuous function on circle, you define its Poisson transform, or Poisson, what's called its Poisson integral, by convolving Poisson kernel against the function. You create this thing called the Poisson integral, and then you, from there, you say that in fact this thing solves the Dirichlet problem. On the disk of radius r0, in the sense that 1, u is harmonic on the interior, and 2, the limit as r goes to r0 is the original function. So there's a way of creating a harmonic function. There's a way of creating a harmonic function on the interior that approaches the necessary boundary values when you do it. So I'm kind of tempted to give the proof of this. In the book they say we do not give a proof of this, but it's pretty cool, and it's very analysis. So maybe maybe next time I'll show you how this works, because this is pretty important stuff, and it's an example of something called approximations of the identity. I don't know if you've heard this term before. Approximations of the identity. The idea is like this. Remember when we talked about convolution, right? That's minus y, okay. You convolve with something, right? And if g of y is like the characteristic function of some interval, right? Some interval. The characteristic function of some interval, right? The average over that interval. Then when you convolve, you recover the average of the function near x, right? This is what we commented on last time, right? This is going to be, we gotta let gn be this, and convolution basically gives you the average value of f near over the interval centered at x. Okay. Now, what would allow you to recover the function exactly if you convolved against it? Okay. What would allow you to recover the value of the function at x exactly if you convolved against it? Can anyone make a guess? It's a little bit funny. You want a single. So as n goes to infinity, and say f is continuous, then this is going to tend towards the value of f at x, right? But I'd like to know, can anyone think of a function that when you convolve against that one function, it just picks off the value at x? Oh. The Dirac delta function, right? The Dirac delta function, right? Which is not really a function, but, right? You convolve against the Dirac delta function, which would say, well, I'm going to be 0 everywhere, but suddenly at 1, I'm going to give you a massive 1, right? Sorry, at 0, I'm going to give you a massive 1, right? And then suddenly, that would give you back your value at x. So the Dirac delta function is the identity function, is the identity in the convolution algebra, right? Convolving against the Dirac function gives you back your function, right? This is the identity element in the convolution algebra, okay? And so these things here, well, these things here, right? Each of them has a mass of 1, right? It's from negative 1 over 2n to 1 over 2n, right? And the height is 1 over n, right? So I'm hoping that the mass is 1, right? And as n goes to 0, right? The mass still stays at 1, but the support becomes arbitrarily small, right? In other words, they're tending towards something like the Dirac delta, which has a support of 0 but a mass of 1, right? A mass of 1 concentrated at a single point, which is impossible as a function. Okay.
What do you mean as a function?
As a function, there's no function whose integral, the integral is 1 and it's 0. The thing is 0. Oops, the thing is 0 for all x not equal to 0. Right. That's what the Dirac delta function basically is. It's something which has a support of 0. It's 0 everywhere except at the origin, and its integral is 1.
Why isn't that a function? Function maps points from one set into another set, right?
What's the integral is, so here it is, right? It's 0 everywhere. It's 0 everywhere, except that something happens at 0, and its integral is 1. Do you know any function that has only is 0 everywhere at a single point, but the integral is 1?
Oh, are we talking about the integral?
Yeah,
The function
the
integral
integral of the
of
function. The integral of this thing is 1. It's not. It's not a function. It's not.
The
there's
integral of delta of x isn't a function, or delta x isn't?
Delta x isn't a function,
So that is true.
right? For any function, right? For any function, the integral over a single point, right? If the integral of the single point is 0, right? If I say the integral from 5 to 5 of anything, right, that's 0.
Yeah, but I could give you a set of, farm animals and map them to their, elements of a set which are what color they are. So a pig maps to pink. You can't take the integral on that, but that's still a function from one set to another set.
So what I mean is that, this is not, this looks like it's a function, right? It's something that appears to take in real numbers and give you back real numbers. Right? This is not a farm animal function. Right? This is actually it's not, it's something like a function, but it's 0 everywhere except at the origin, and its integral is 1. Okay. But it's not a function because there is no function that has the property.
Wait.
Could it be a function on the hyperreals?
There are two ways of looking at this. One is that it's a measure. It's a measure. Okay. Another is it's what's called a distribution, a generalized function. But that is something that you integrate against functions. Something like a measure. But anyway. So long and short is that there's this thing that you'd like to convolve against. The Dirac delta function, which is not a function, is the identity would be the identity for convolution. Okay. And what happens here, is that the Poisson kernels, are all in the limit approaching the Dirac delta function, just like these things are approximations of the Dirac delta function. Okay, so it's a technique called approximations of identity, which allow you to recover your values of the function. Well, maybe we'll talk about it next time. It's pretty important. Okay. Okay. Yeah. So, okay. So, at this point, I'm afraid for those of you who've had some analysis before, we're going to have to go a little bit backwards and talk about sequences and series. But we're going to go. Don't worry, we're not going to spend too much time on this. We'll get the necessary ideas for those who haven't seen this stuff before. So a quick review of sequences and series. So for those of you who've seen it before, it may not be quick. For those of you who haven't seen it before, it may not be review. Okay, so as you know, right, the sequence of complex numbers. Sequence of complex numbers, and what we said before, right, if there exists a point such that given any epsilon, there exists time such that whenever you're past that time, Zn minus Z is less than epsilon, then we say Zn converges to Z. Zn converges to Z. That we said before. Right. We also mentioned before the notion of a Cauchy sequence. Zn is called a Cauchy sequence if given any epsilon greater than 0, there exists an n such that if m and n are greater than n, then Zn minus Zn is less than epsilon. Okay, so Cauchy, converging, a convergent sequence means that, given any epsilon, you can guarantee there's a time past which everybody is within epsilon of the limit. Cauchy sequence means that given any epsilon, there's a time past which everybody is within epsilon of each other. Okay. And the thing about the complex numbers is that a sequence converges if and only if a sequence is Cauchy. So all sequences, all convergent sequences are Cauchy. All Cauchy sequences are convergent. We'll be more concerned in this course with series. If you have a sequence of complex numbers, then you let S of n be the sum of the first n guys. So then this new sequence of numbers is called the sequence of partial sums. Right, the sequence of partial sums of the original sequence. Right. So you sum the first n guys, and you look at the partial sums, the sum of the first guy, the first 2 guys, the first 3 guys, the first 4 guys, etc., etc. And that sequence, you're wondering if that tends to something, right? If as you keep on adding on more and more guys, does that tend to something? So if the sequence of partial sums converges to something, we say that the infinite series converges. The infinite series converges to this. Everyone, it's okay? Okay. Nothing fancy, right? You have your sequences, and then series are just sequences that you make out of sequences, right? It's a sequence where you take one sequence and then you start, you say, I'm going to let S of n be the sum of the first n terms. So you create this sequence of sums, and then if that sequence converges, then you say that the infinite series converges. The infinite series of the original sequence converges. Okay, so then you take the Cauchy, you take this Cauchiness, right, and you translate it in terms of series, right? So what does the Cauchy what does Cauchiness mean for series? This is called the Cauchy Criterion. It's just a translation of this statement in the language in the setting of partial sums. Okay, so right, a series, an infinite series converges if and only if, given any epsilon, there exists an n such that m and n being greater than n implies that the sum from I equals n to m, and let's say that m is bigger, it's less than epsilon. So this is exactly the same statement because this converges. This thing converges. The convergence of this is to say that the sequence of partial sums converges. Right? Right. If this converges, that's by definition that means that the sequence of partial sum converges. Right? Well, by the Cauchiness, that's to say that S of n is Cauchy. Right? Because we know that everything converges if and only if it's Cauchy. Right? What does it mean for the sequence of partial sums to be Cauchy? It means that given any epsilon, there must be an n so that the difference of the partial sums must be less than epsilon. Right? Right? In other words, Sm minus Sn must be less than epsilon. From n to m minus 1. From n plus 1 to m. Right? This is the sum up to m minus the sum up to n, and so this is the sum from n plus 1 up to n m of that. Right? So it's just all we're doing is just translating. All we're doing is just translating. Okay. So in the setting of series, the statement that a sequence converges if and only if it's Cauchy says that a series converges if and only if its sequence of partial sums is Cauchy. In other words, given any epsilon, there's a time past which any of these partial tails are all small. Okay. So that's pretty useful. The Cauchy criterion for series. For example, the divergence test. Right? If a series converges, that means that the limit of the terms must be 0. Right? Why? Right. Given any epsilon, we know that there exists an n such that the sum from n to m of z sub n is smaller than epsilon, right, for all m and n bigger than n, right, by the Cauchy criterion. So if Zn converges, then it satisfies the Cauchy criterion, right? And so we know that given any epsilon, there's a time past which these partial tails are all small. Right? All the partial tails are small. Well, we could just take take m to be equal to n, and that would say that Zn in particular, the partial tail consisting of one term, right? Consisting of one term, each of the partial tails consisting of one term must be smaller than epsilon, right? And so what does that tell you? That tells you that the sequence goes to 0, right? Because you found that for any epsilon, there's a time past which the modulus of each term is small. Right? In other words, the limit is 0. Right? So, simple consequence of the Cauchy criterion for series. Okay. Absolute convergence. Absolute convergence. What's absolute convergence? You know what it is. What's absolute convergence of a series? It means that
Absolute values converge.
the absolute values converge, right? Definition. If the series that you get by taking the absolute values converges, we say C sub n absolutely converges. Okay. You probably know some examples. Can somebody give me an example of a sequence of a series that converges, but not absolutely? -1 to the n over n. Yeah, that's good. Right. So this one, if you take its absolute values, you get the harmonic series, which diverges. Right. This series doesn't converge. But maybe you remember from Calc 2 that this series is if you look at the original series, right, it's an alternating series with decreasing sizes, right? And that series actually does converge. Okay, so you can have a series that the original series converges, but it doesn't converge absolutely. However, if the series absolutely converges, then the original series converges. So if the sum of the absolute values converges, then the original guy converges. And one way of saying that is using Cauchy. A nice way of saying that is using Cauchy's criterion. You say, well, look, if this thing converges, well, then by the Cauchy criterion, right, given any epsilon, there's a time such that if you're past that time, then the sum of the tail is smaller than epsilon, right? That's what the Cauchy criterion says, right? But if that's true, then the sum of the original guy is definitely smaller than that. The partial tail for the original guy is definitely smaller than that, and so that's smaller than epsilon. And by the Cauchy criterion, that means that the original guy must converge, right, by the Chern inequality. Right? So immediate, right? Cauchy Criterion says, right, if this thing converges absolutely, well then, that means that given any small number, there's a time past which the partial tails are smaller than that. But then you notice that that implies that the partial tails of the original guy are also smaller than that. And so the original guy satisfies the Cauchy criterion, and so it converges. So, but then the original guy also satisfies the Cauchy criterion. The triangle column. And so it converges. Okay. Okay, everyone all right? Okay, now we're going to go to uniform convergence. Okay, so here's a crucial notion for us in complex analysis. Uniform convergence. So I'm laughing because this is like we're going like at the speed of like of a racetrack. Okay. Okay. So here's the idea. You have a bunch of functions. You have a sequence of functions now. Okay. Not just a sequence of points. You have a sequence of functions, and you have some last function. Okay. If given any epsilon, there exists a time such that past that time, fn of z minus f of z is smaller than epsilon for all z in your domain, then we say f sub n converges uniformly to f. Okay. So let me give you an example. So if you look at, say, f of x being x to the n, fn x being x to the n on 0, 1. Okay. Then here's 0, 1. Here's the first guy, right? X to the 1, x squared, x cubed, x to the 4th, x to the 5th, x to the 6th, etc., etc. Right? And you see, as time goes on, right? As time goes on, then at each point, right? If I take any point here and I look at fn x, as x goes to infinity, right? Except for 1. Let me just ignore 1 for now. Okay. If I look at any point, then what's the limit going to be?
0.
Be 0, right? It'll be 0, right? But there's something not uniform about the rate of convergence, right? These guys here go in faster than these guys over here, right? These guys here go in faster than here, so what happens at what happens to the last point? I already wrote it up already. It's 1, right? Right. For the last point, everybody just stays at 1, right? So, right. If we took the limit of these, if we took the limit of this, here's the limit, right? It's going to be 0 everywhere, and it's going to be 1 over there, right? This is the sort of like the limit of the f sub n's, right? Here's f1, here's f2, blah blah, and f is the limit. Okay, but you notice that I can't if I say here's an epsilon, I'd like you to find a time past which you know, everybody, all the f sub n's minus f are less than epsilon for all x in the all x over this interval. You can't do that, right? You see that? There's no time that's gonna there's no n past which that will work. Let me give you an example of something that actually is uniform convergent, right? So if I had something dumb like this, so suppose I let f sub n be just the constant 1 over n. Okay. So at time 1 it's this, at time 2 it's this, at time 3 it's this, at time 4 it's this. It's just dropping. Okay. Right. And then you notice for this one again, you know, the limit is the limit function is just going to be the 0 function in this case, right? Okay. And you notice that if somebody said, I'd like you to find, I'm going to give you an epsilon, can you find a capital N so that whenever n is bigger than n, all your values are close to the limit value? You'd say, yeah, I can do it, right? I can do it. All I need to do is to take my n, you know, bigger than 1 over epsilon, right? And that'll do it. Right. So there's a uniformity to the convergence here, but there's not a uniformity to the convergence here. Okay, and so that's the difference here. That given any epsilon, you have to be able to find a time past which all the functions past that time are close to the limit everywhere. Everywhere. Okay, everywhere on the domain. That's the thing. It's the convergence is uniform. Okay. Are you getting a notion of this thing? So this is what's called pointwise convergence. If you look at each point, oh yeah, the values are going down to 0. You know, this is pointwise convergence. This is better than pointwise. It's pointwise, but it's also uniform. Okay. The limit, you know, the limit at each point is f of z. But better than that, you can control. You have control over everybody in the domain. You know, you can say past a certain time, everybody is close to this f. Let me show another picture. Uniform convergence is basically like this. Here's your f. Here's your f. And you put a little tube around f, an epsilon tube, plus epsilon minus epsilon. Okay. Uniform convergence says that given any epsilon tube, there's a time past which all the graphs of the guys lie in the epsilon tube. That's exactly what this is saying, right? You know, given any epsilon tube around the graph of your function f, there's a time past which the graphs of the functions past that time all lie within the epsilon tube. Okay. And you see why that works here, right? I have an epsilon tube here. Eventually, you know, I can find a time past which everybody's in the epsilon tube. But over here, it doesn't happen, right? No matter what I do, well, no matter what time I choose, well, there's going to be some trouble over here. Okay, so that's called uniform convergence. There's a funny notation for it. I've only seen this a couple times, but it's kind of cool. Double arrow. Fn converges to f. Fn converges uniformly to f.
What would non-uniform convergence look like for a sequence of functions, though? Because this is pointwise.
Yeah, but this is not uniform.
Right. Oh, okay.
Yeah, this is not uniform.
But you can say in this case that the sequence of functions Fn converges to that.
It does. It converges, but it doesn't converge uniformly. Yeah. So pointwise convergence does not imply uniform convergence. Uniform convergence, however, does imply it means that you do converge pointwise. Okay, and this distinction will be really crucial for us. Because what we'll see, roughly speaking, is that for analytic functions, uniform convergence works sort of works really well with differentiation. Okay, that is, what will happen is that, so let me say it this way. In real analysis, so for real value functions, if you have S of n all differentiable functions, and they converge uniformly to some f, f doesn't have to be differentiable. It's not true that uniform, if they converge uniformly, that the limit is still differentiable. It's also doesn't also false. Not true that the derivatives converge to the derivative. Right? Even if f is differentiable, it's not true that the derivatives are going to converge to the derivative. Okay. But what we'll see for analytic functions, given some condition, are that if your functions are analytic, then if they uniformly converge, then the thing they converge to is analytic. Further, that the derivatives will converge to the derivative. Okay, so it's much better. That's the theorem of Weierstrass, which we'll see next time on this. Okay. So uniform convergence will be really important for us. Okay. So let me put up a Cauchy criterion. So there's a Cauchy criterion for uniform convergence. Which goes like this. A sequence converges uniformly if and only if, for all epsilon greater than 0, there exists n such that n being greater than n implies that s of n z minus s of m z is less than epsilon for all z in your domain. So it's sort of what you might expect. Right? That you satisfy the Cauchy criterion uniformly, right? You satisfy your Cauchy criterion uniformly, that means you converge uniformly. Okay. The proof of it is not difficult, so maybe I won't talk about it. But let me state and maybe prove some important facts about uniform convergence. One, if you have a sequence of functions and the Fn are all continuous, and two, the Fn converge uniformly to some f, then that f is continuous. So uniform convergence of continuous functions will converge to a continuous function. Okay, so continuity, does behave well. Second thing, if you have some functions on a real interval, say, and they're continuous, if the S of n converge uniformly to some f, then the limit of the integrals actually is the integral of the limit. So uniform convergence allows you to commute differentiability. Commute the integral with the limit. you notice that, remember what we said earlier, that for real functions, it's not true that the derivative of the limit is the limit of the derivative, because the limit may not even be differentiable, right, for real value functions. But for continuity and integration, we do have some nice results like this. So yeah, I guess I'll stop here, and we'll talk about that next time. So next time we'll talk more about uniform convergence, in particular the Weierstrass M-test, and also Weierstrass's theorem about the preservation of analyticity when you have uniform convergence. Okay.